later on, you are going to implement a system as it was there planned. Yesterday, we were talking about architecture. So you know that there are a couple of things. First of all, you need features. So from the stored template, like let us say we are talking about verification. So for your template, which is stored in the database, and your template, which you are giving at the runtime. So those two those two templates are supposed to be matched. So when we go for machine learning based system, those features are handcrafted features. And if you go through the machine learning or pattern recognition literature, the literature is full of handcrafted features. So people have developed features for specific applications and they have shown that this is working well. But if you go for, okay, let us say uh, the feature on which people are agreed. So let us say shift features, they are very popular texture features, which are being used very extensively in this pattern recognition application of biometric. Now, so then we need a matcher. So and threshold, as we discussed yesterday. But what happens when we go for deep learning based system? Because state of the art systems are deep learning based systems. Here we do not have handcrafted features. There is a neural network, right? Deep neural network, which is extracting features. So here, this demo is there so that you will get an idea, and then it will be easy for you to implement. So you can see that here, phase one, that is the architecture. So one architecture we have taken. Here you can see that convolutional layers are there. So input image, you can see here, the input image is there, followed by some layers are there. And finally, when we go for the output feature, so we get feature embeddings. And then you know that when a template is created, so a template is an amalgam of the features which you are giving at the time of registration. So you are giving, let us say, your fingerprint at different angle. So the features are being extracted. So feature embeddings are created corresponding to your, let us say, several biometric data. And then a template is created from that feature embeddings. So here it is being shown that now, as we know that in the convolutional neural network or deep neural network, we learn the hierarchy of features. So you can see that here when we are at the this first two layers, convolution layers, we are learning edges. Then in the next, we are learning shape. Then so gradually, and finally, you can see that semantic. So at the end of the this output, what we are going to get? We are going to get features corresponding to, means the important distinguishable information from your input biometric. So here, if you go, all the details are given. You can see it. So you can see that the purpose of the layers is given there. Now, here the thing is that when you are going to train, then yesterday, Dr. Kiran Raja has used the word that is the triplet loss. Like how to, because those who are knowing deep neural network, they know that we are going to minimize the loss over there, and that is how our network is learning. So we have some uh, loss functions, right? So here, when we are learning a biometric template, basically what we want that our own template should be closer, like the features of my template should be closer, and the features for my template and your template, they should be far away. So we are using a couple of loss functions over there, which are meant for it. So triplet loss is one of this. And here, in this example, we have used this, I think, just a minute. Yeah, just a minute, let me show you. So what happens here after architecture, now you come to the training process, right? So this is your architecture. Now in the training process, you can see that this is your data. So these are the data from the same person. These are the data from the other person. So as you know that at the time of registration or enrollment, multiple, you are providing your own data multiple times, right? So that is over there. And then, so if you go through that, and then the embeddings are going to be created. And as you can see that the embeddings which are going to be created corresponding to your own templates, they will be quite similar. Let us say similarity is here 95%. But if the embeddings of the other, like different users, you can see it is around 30%, right? Now you can see that what happens here in the training. So here in this demo, the loss function is used as phase, and this is some loss functions are given by different researchers. So here this loss is working very well for phase biometric. Now you can see here in the deep neural network, we know that there is a forward pass, backward pass, and you can run it here. So we can animate this training process from here. So just a minute. Yeah, see, you can see here training log is generated. So now your neural network will be learning here, so that your template as well as like other users template, and now you can see that what is happening. This is the embedding space. So you can see that these are the template of one user. So they are these are the feature embeddings of one user. So they are very close to each other. These are embeddings of the other user. So you can see that a simple demonstration is being done in this demonstration is shown you in the 2D space, but how features are being extracted? This is a 128 dimensional space. So like we all know that in a 2D space, what is happening? There is a point. So we know that, okay, this is the X value, this is the Y value. Now just imagine that in place of X and Y axis, you are having 128 axis. So there is a point which is having a value for each of those 128 axes. We cannot show it visually. So visually it is just shown for two-dimensional. But that is how you can say that these are the feature embeddings corresponding to this user. And by taking averaging, or I mean considering these embeddings, this is the template you can say is created. So whatever features are extracted through that embedding, considering that this template is created, and later on this template, right, these 128 dimensional, right, these 128 values will be used for matching. So that at this template is being stored. So what does it mean? That corresponding to your biometric, these 128 values, right, are being stored. And when you will come for testing, then again you will give your biometrics, your feature embedding is going to be created, and those 128 values will be compared with these 128 values to by matcher to get the similarity. So here you can see that verification. Now you can I mean you can test it for the same person. So let us say I showed you the inputs over there. So their template is stored. And let us say I'm running it for the same person. And the similarity which we are using here, that is the cosine similarity. In my next talk, when we are talking about biometric system evaluation, I will tell you about these things. So how a matcher is going to generate the similarity value. So here you can see that when we are testing it, so with the same person, then what is happening? The similarity is high, not 100%, remember here, but it is quite high, 98, more than 98%. But when we are going to test it for a different person, now you can see the similarity, right? So then the different person, so the two, they are not matching, and the access is going to be denied. So you can, and then so complete flow is given here. You can go it like, and whatever process I have explained you, your Dr. Kiran Raja, he is going to implement it with the images and every network and everything which is uploaded on the drive. So I hope you got an idea what you are going to do. So this is the whole flow. So you need a neural network. You are going to train that neural network using the input data, the whatever you are taking, face biometric or fingerprint, whatever. And then so your model is learned, and your templates, if you are going for a verification system, so your templates are going to be stored over in the database at the runtime. Again, that neural network is being used to extract features, and then the matching is performed. That is the whole thing. So I over to you, Dr. Kiran.
Morning. So, what we will do today is that all this process that has been shown is something that we will take a look at. There are two demos that are uploaded. One is the demo that is on deep learning based face recognition system, and the second one is the classical machine learning. I think Professor Preeti Khanna already has this one, where it shows number of different pipeline. And this is what you typically see in the fingerprint authentication system. So we will build upon the fingerprint authentication system later for the second session. But I just wanted to take some time to walk through the code for the code that is related to this deep learning based biometric system. Okay. Okay. So let's start with something very simple. It's no, yeah, you can take your time. You're taking your time to set it up. I could just walk you through the code that Professor Khanna just mentioned about. And the first thing, let's take a look at the backbones. So able to see the at least the code, right? The first part you're able to. So the architecture that we were referring yesterday is the first part of convolution, right? So we were discussing about how to extract the features from the face image, and then in that one we were showing we could have Gaussian blurring or Sobel filtering, or in the best cases we have this convolution filters, which typically is defined by what is the size of the filter. So when we talk about the size of the filter, we are talking about the size of the filter here in this case 3, and then it tells how many planes go inside and how many planes come outside of that convolution operation. And then do we need to do stride and dilation? And then we have the similar configuration for multiple things, right? So here, and then in the basic block, we are kind of configuring all the different operations. So we are starting with something that is very simple, which is batch norm in the 2D space. And then we are trying to introduce one convolution, and then followed by second convolution, second followed by the batch norm of second convolution. And then there is a ReLU, which is kind of activating the outputs. And then we go for another batch of convolution, batch normalization, and so on. Now, what is important here is to understand that this architecture is not a universal architecture, right? So it might be very much varying depending on your use cases, depending on what is working for what kind of data. Okay. And then if once you have all this thing, again, you have you can kind of define the forward passes in different blocks. Again, here, this is a simplified version of the ResNet, which is a smaller version, which is iResNet. And then this also comes with 3 different architectures. One is 34, 50, and 18. So everything is, again, as you can look from here, uh, you should not probably try to run this part of the code because it's going to not converge immediately. It will take a long time. So run it when you have time, and then when you have the whole database set up. So at this point of time, you can see that the configurations can vary a lot for different applications. Now, if you go from this one to something more compact like MobileNet, so the architecture will be very different. Huh? But what is important, remember, you could use any of the existing networks, existing architectures, and then adapt it to your own network, your own use. Sorry, right? Okay. So this is the part, and if you look into the code, I'm also in the face feature extraction. I've also provided the link to the paper. And in the link to the paper, if you go through that, and that explains all the things that are happening inside that particular network. Now, another thing that is also important to remember here is that all the most modern architecture that we're looking at, that is arc phase, cos phase, and variant of that, they're all based on very simple architecture. The only last part where you have the loss, which vary. In one of them it is arc phase, the other one it is a bit of elastic arc phase, or some of them it's triplet matching, as Professor Khanna was mentioning before. So these are the changes that you have inside the training process. Okay, good. So then I have also to show you something about the, and also in the same course, we have provided two different pre-trained architectures, pre-trained models. So the pre-trained model is provided as a PTH files, as you can see here. This is for the arc phase. And then a similar one, the most recent paper, which is on CVPR 2022 or 2023, that is called elastic phosphase. And here also we have provided one backbone path. Okay? And there are multiple backbone paths. If you go to the official repository here, you can see different snapshots of the same trained model in different epochs and different stages. And then here, just to go back to what Professor Khanna was mentioning, so here you can see that how many hours it nearly took. It took approximately 57 hours for training the whole network. So do not start it while you are running the course. For the time being, just trust us that this will work. And the only thing you have to do is to use the network to test the images. Okay. So here you can see in the first part, the loss is around 39.1512. And as the training progresses, the loss starts getting lower and lower. And now you can see that it becomes around 19.80. And then further, if you go down towards the end of the, ah, and while once one particular epoch is completed, and here you see that the accuracy is around 0.99, and then the x norm is around 19. X norm is nothing but the distance in the space. And then you have, these are all for the different data sets. And here you see that while you're training, you can be training on one data set, but at the same time, you can be testing on multiple data sets in one instance. So what we want is we want a network that can scale up across all different networks, right? Sorry, all different databases. So for every iteration that we are doing, we are seeing that, okay, in the first case, we have around LFW is a database which is labeled phases in the field. And then we have the CFP data set, which is another very well-known data set in phase recognition. And then HDP has the age progression. And then we have the CALFW, which is a celebrity version of that one. And for every single thing, you see the accuracy is kind of varying, right? Now, what you should also notice here is that some databases might be very easy to solve. So in the first case, LFW, you're already getting around 99% accuracy. Beyond that, you can get maybe marginal improvement, not significant improvement. But on the other side, if you look at the CALFW, the accuracy is around 92. And in the previous case for the HDB, it is around 90. Now what you do, either you can stop the training here, or you can restart the training from the same epoch, which means now what you're going to do is you're going to update the parameters. Right? So once you start updating the parameters again, let's take a look at the next set of training. And when you go to the next set of training here you can see that the accuracy of this one also went up 99.317, while the one that was struggling before, that was 92%, now it has also been right. And then now what you do is that you kind of continue the training over and over again until you come to a place where you're satisfied with accuracy. Some tips and tricks here is that you should also remember that sometimes the accuracy might not improve at all. It might stay stagnant. So at this point of time, you might have to make a decision telling that, okay, should I continue training it further with no gain, or should I quit it, and then should I change the learning rates? Right? Now you know what the learning rate is, right? So how often the weights are getting updated and how they are getting, right? So there is a parameter called learning rate, and that helps in improving the performance here. So if you take the whole code base and then keep running this at some point of time towards the end of the training, let's go back, let's go to the end of the training. And here you see that the highest accuracy that we could achieve was around 99% for the LFW dataset. And for the CLFW, we could achieve accuracy of 96%. So that's the maximum, right? I mean, you could extend it beyond, but at the cost of maybe 0.001% improvement, which is not really significant. Okay, so this is the training log for this particular version. And again, as another a small tip here is that whenever you are training, at least in this kind of the networks, right? So there are a number of things that we are taking into consideration. So for instance, here we are configuring what should be the size of the embedding, the one that we mentioned. In the demo that Professor Khanna showed, it was 128 dimension vector. In our case, here setting it to 512. And here also, there are some other factors for the optimizer. What should be the momentum? What should be the weight? And so on. Uh, Another critical factor that we have also noticed in training the face recognition system or any other system is the size of the batch. Here, right? So we say that how many images should go into the batch. So and then how we could use it for updating the batches and things. Okay. Um, what is specific to this cost loss and the arc phase loss and the cost loss is this two factors, which is called as S and M, which goes back to the equation in the paper that you see. This can also have a role in convergence of the network. So most of you might not be training your own networks because you'd be starting from something that is existing and then use it for your application, right? So with that being said, you can now think about one more thing here. Probably the other aspect is that I told you before, you do not really need to create a new architecture for the whole case, so you can reuse the architecture. You see it here, and in this case, I'm setting it as okay. Use the ResNet, and then from ResNet on, you can start fine tuning the weights, right? Or if you want a compact network, you can say I would want a mobile face net, and the mobile face net has an embedding size of 8 as compared to the ResNet, which had the 512 embedding space. Okay. Um, okay. These things are all very specific to your training, so I don't want to spend time on this one. But if I just go back to the now, if I go back to the backbones, let me see. Okay, so if you're all ready, so we could take a look at this, how the whole pipeline happens for face recognition. Ready? Okay. Okay. So the first is the name of the file is called face feature extraction and comparison. So the first file is typically what is called as the first part is typically what is to import the libraries, right? So we want some libraries to run the code. So I can say that, okay, just import those libraries. And then um, remember the image that is a matrix use internal. And this is the place where we're converting an image, then making it a matrix. So there are small details here. One of the detail is that first you want to read the image, and when you read the image, you read it as RGB because a color image is three-channel. And then um, the OpenCV version of the image reading has a slightly different formatting. So it might be from RGB to BGR. So make sure that you are looking at the documentation of how the images are. Okay? Otherwise, you will get very corrupted channel when you look at it. Okay, and then once you have that, here what we are doing is like we want the network to handle the same set of information, right? The same size. Even if your camera is capturing it, 512 MB or 1 megapixel, want to reduce it to one standard. And these networks are trained on 112 cross 112, so we are just resizing. And once it is resized, uh, again remember that the image is typically RGB, which is three channels, 112, 112, and 112, right? So what we want is that we want them to be in the different order for this kind of architecture, and we are just transposing the link. So what we are doing is we are bringing the channels first and the spatial network. And then what we are doing is that we are just converting it to a tensor. Tensor is nothing but a 3D map, right? So it's a arranged map. And once you have that, we also want to make sure the data that we are dealing with should be scalable, and to make it scalable, make it manageable in the network. So we are just dividing it by 255. So everything turns down to 0 to 1, and then we rescale it back to -1 to 1. So which would mean if you have a pixel which is extremely white, in your case that would be 1, and the pixel that is black, that would be -1, right? It's only the stretching and scaling. Okay. Now, assuming that you have trained a network that is that you're then the first thing that you would want to do is that you would want to load the backbone model. So what do we mean by backbone model? We want to look at the configuration of the entire architecture. So the way that I had defined in the previous case, for instance, if I go back to this here, so you remember the architecture that that we had said. We had said, okay, the first layer should be convolution, the second layer should be bash norm, and the third layer should be ReLU, and so on. So this has to be informed to the network again. So whenever I'm rerunning the face recognition system, so that is the first thing that I'm going to do. I'm going to say, okay, from this particular network, import the backbone, and the imported backbone is initialized in this case here. Now you see that I'm very specific to the architecture. I'm saying, okay, use the architecture IResNet 100, and then I'm telling I would, in this case, I would need 512. Because remember, in the previous case, we also said number of features could be configured. I could tell I want 128 dimension or 512 dimension, right? So in case if your backbone that is trained and the number of features that you're demanding here are not matching, the network will crash, right? I could also show that very quickly here. So assume that I'm going to put it as 100. You see that? So there is a mismatch of the configuration. So whenever you are training a network, it's also very important to disclose the configuration of your network. So now if I go back to this one and I simply say quite well, and then if I'm running this, now everything should work. And here you can see the entire architecture of the network. It's a very long architecture, but you see that what is happening in the module one, it's IResNet architecture. And inside the IResNet architecture, you have multiple configurations. And then it continues all the way to the end, and it tells at the end of this last layer, the FC layer, you're going to get 512. Make sense? Okay. So now again, in some of your own use cases, maybe this architecture might not be optimal. So you might want to investigate some more time, put some more time, and try to modify this architecture. Okay. Good. And now, unlike the second part that I also want you to understand here, as you can see, it's a very long architecture. Here. So this is where I'm saying the configuration, and then here you see that I'm loading the previously trained weights. That you spent like 8 hours to train the network. The weights are stored, and the weights have to be loaded back into the network. It has to be initialized. Okay. Uh, Now, at the same time here, there is a misconception. Probably many of you might think that you would need a GPU to run the code. That is not necessarily. You can train it on a GPU and set it also on run it on the CPU. So this is what we are doing. In this case, we are just setting it to CPU, and then this is just a specific call to the model. But whenever we are running it for deployment purposes, your authentication system is actually running, then we always set it to evaluation. Right? You see this one here. So this is typically the evaluation mode. And just to give a small introduction how it looks in a training, I can go back to this training model point of time. So there is a script called as train.py. So in the train.py, it's very similar to what we discussed everything here, except the fact here we are setting it to the configuration. And then what we're going to do is that we're going to set backbone.train, and the train function is called so that all these operations are happening. And now if you look here, there is no way where we are calling the eval function. So this is, in fact, this is the file that. Good. Then we have, if you take a detailed look at this one, right, you can see that. No, you're taking a different data set, the one that I showed you, LFW, CA, LFW, and so on, and then you're trying and check what is the performance improvement in every single stage. Okay. Okay. Remember, in this case, we are just calling the model.eval. And now once I have this one, what I could do is that I could go to the next part here. So now data set here. Um, One small comment here is that you see that from the folder is called align. It was one of the steps that we did in the previous case, right? Because LFW is it's a database which is scraped from the online, so people have different poses. So we have tried to align them, all of them. And then the first thing that I'm going to do is that I'm reading the image. The image is being read here, and then I'm converting the image into a tensor. And once I've gotten the tensor, then I'm going to send it to the model that I actualize. And then to make the life simple, what I'm going to do here is that I'm just storing it as an NPY, but this is not a necessary step. But if you're going to rerun some experiments later on, so it's also smart to just store it as an NPY file or any JSON file, text file, whatever is your preferred file. Okay. Here are the places where I'm going to extract the reference images. Okay, I think I did not run the image sensor. Let's go back and run that one. So now I ran the image tensor. This is the data set, right part to the data set. Let me just get the data sets. And then I have the file name here. And then I have the path. I'll just copy the path. Okay, let me just verify this works. Yes. So now you see that it actually demanded the full path. So I'm just going to give the full path. So when I've done, so if everything worked fine, so here I should be able to see two NPY files. Now you see that there is a probe LFW features.npy, and you see there is also a reference LFW features.npy. Okay, so now out of curiosity, if you just want to see, you can also go in and see with any of the editors. Let's see with this one. With this one, you probably will not be able to see anything. But if you open it in as a data frame, you will be able to. Okay, good. So now that I have extracted the features from the train model, now I can simply do a Boolean matching, right? So I can say that, okay, what would be the distance between the two images, between these two feature vectors. And now if I just run this one here, so let's say torch dot load. So this is just loading the image back, loading the image back. Now I'm seeing the similarity score is 1, right? So now the similarity score is 1 mainly because I'm using the same image. So now curiosity, let's try to match two different people. So I'm going to take from the data set here. I'm going to take some random person here. And what I'm going to do is I'm going to only change this person. So I say now two of the reference file remains the same, only the profile changes. And now if I go back here and then compare them, now it's that the score is -5, right? So now I think when in the next part of the lecture, you will understand how to set the thresholds. But just to show you how the thresholds actually work, let me go to this one. Okay, now before we go that, so I know that exactly I should reject someone. Anybody had some idea? Threshold? Yeah. How do we determine this threshold? After multiple experiments, right? So we need training data set, and on the training data set, we kind of identify, okay, what is the best place where we're getting lowest error rate. Once I know the lowest error rate, I can set that threshold one here, and this is what is your practical biometric authentication. And again, what happens in the practical word deployment is that you might start with some threshold which say 0.75, and then later you detect that, okay, it was not working in the lighting condition, it was not good, and then you can go back and refine it all the time. You start with 0.75 and then you keep on updating. Okay, so now just try to run this one, and then we could also take a look at the fingerprint before we start the next part. So is there anybody having any trouble? So you want to run that, check that? Yeah. Also, just as a spoiler alert here, right before the next lecture, this is how you would probably plot the entire training process. And after the training process, you would measure the biometric error rate. Once you measure the biometric error rate, you can see that the lowest error rate that came was around 20%, approximately 20%, and that is where you would pick your threshold. Okay, so now if you take the next system, in the next system you see that it's quite bad, right? Actually, it's quite good. So it is in 0. Okay, I could also show the fingerprint-based system if you are working on the right now. Base. Yeah, it will take good. So then I can show you this a similar thing for the based authentication system. Remember, we spoke about multiple systems yesterday. We saw that, or we discussed that it could be either face-based system, based system, or voice-based system. Compared to the deep learning-based system that's used in the case of face recognition, in the case of fingerprint, we are doing still classical. At least in this case, we are taking the classical example, and which would mean we would extract minutia information. The minutia information, I'll discuss about the minutia information and rest of the things later. But just all these things are done in offline, but all the codes and the file are available on your Google Drive. Um, Let me just show you what happens in this case. Okay, so here this is the fingerprinting, right? For the time being, just ignore the color just because of the visualization. We have put some color there, and now if you go down here, here you can actually see what features are we looking for. In the previous case, we let the network learn all the features by itself, right? So in this case, we are actually going in and then trying to look for the features that we think are relevant for us. This is based on the way the humans actually compare to. Okay, and then in the previous case, we were also doing some cosine distance similarity, right? So cosine similarity is very nice when we have fixed length vector. So all of your deep learning systems will give you fixed length vectors because we said we want 512 features. When we are trying to implement that for fingerprints, so for the fingerprint one, maybe I get so many points. For the fingerprint two, maybe I get only these many points. Right? You can see that some parts of the fingerprint might be missing. That means the number of points that I'm getting actually will also be missing. So when two unequal length vectors, can I use cosine distance? It's difficult, right? So I can come up with some tricks to do some matching, but normally if you go by the books, you cannot really do that comparison in the two varying length vectors. So what do we do here is that we make use of another kind of matching, and this matching is based on x, y, and theta. Again, the idea here is that depending on the model that depending on the mode that you're using for authentication, fingerprint or iris or face, you might also get all these components. Yeah? Now, if you do all those aspects here, if I just run that one quickly, you can see that it uses a file XYT, which is X, Y, and theta, which is where the point is being located and which direction it is pointing. Yeah, which we will discuss about this later in the evening, in the next part. But the idea here was to just introduce you one classical approach, one deep learning based approach. So in the deep learning based approach, we introduce face. In the classical machine learning, we are using the fingerprint. It needs exe, right? Because it's not present in that one, so I can upload that one. So I have uploaded probably the Linux version of the. I can upload them. Okay, good. So again, I think yesterday or day before yesterday, I was mentioning about something. The state of the art matches here. There are a number of matches for the fingerprint which are available on the NIST website. So this Bozart and MinDTCT, they're some of the algorithms that are developed by NIST, National Institute of Science and Technology, no, Standards and Technology. Uh, they have provided the EXEs which can be used for your own purpose, okay? Typically for non-commercial, but it gives an idea. Okay, and then in your authentication system, just for the sake of But if I have my own finger matched with my own fingers, so I should be coming in somewhere in this area. The spread is quite wide. But this also should give you an indication about this area, which is typically the area for fingerprints which are not completely distinguishable. The score, the matching score, or the comparison score might be extremely low. Right? That's why it's going towards 0. Okay, so this is what I wanted to show for the authentication part. Um, you can go back and then re-implement your own system. So with the print system, I also given one data set that you can use. For the face, you can download the data set. If you're not able to download the data sets, you let me know so I can upload the data set. But I'm not allowed to redistribute data sets. But for the sake of experiments, I can give you at least a part of the data set that you can use. Okay? But LFW is provided in the core. Uh, Min DTCT, right? So let go through VDC. Okay. Now you have both the Windows version, right? Okay, for those of you who are using running the system, just you can try to upload your own images and then try to see how we get the scores. Try to do it for different days. Take an image from today, take an image from I don't know 5 years ago, and then try to see how good the score varies, which we'll also use for later discussion how the score can change over the period of time as the age progresses. Good. Any questions so far? Yes. Okay. For those of you who are doing the deep learning, the question was that instead of manually changing date, can we use some schedulers? So today there are a number of very good schedulers. So you look at the whatever the metrics that you're looking at, either the accuracy or the error rate and so on, and change the scheduler rate in the schedule. This rather than checking it manually. Yeah, I've given the train model. This is the train model here. So there are two train models. So one is the train model from Elastic arc-based train. Yeah, yeah, yeah. So you have the train models, right? So go to this particular block. So here, if you go to this block where I've said load train CNN model along with the weights, and then in our case, we are making use of ResNet 100, and then I'm uploading the image using the CPU, not the CUDA. But if system has GPU, then you can use CUDA instead of CPU. Okay, and then once you do this, go to your own images, load the images, and then try to see how much of comparison score you're getting. Yeah. No, many of these data sets are available. So align versions that are available. Again, maybe if your architecture is invariant to the angle and pose, you do not need the alignment, right? But most of the cases, in most of the practical biometric systems in face recognition, your passport image is always frontal, right? So you want to make it compatible for those kind of images and also for the noisy. So you can either make a choice in the architecture, or you can say that, okay, I want all the images to be aligned. Mm. Yeah, yeah, yes, yes, yeah, yeah, yes. Okay, yeah. So here is a very interesting question. So the question is about if we have use in A, B, and C. So what I can do is that I can train the A and then validate on the C, right? Or I could also say the other way. I could say that I split 20% data from A for validation. Then I'm just sticking on to one data. So either of the both the approaches are quite okay, but just remember that your network becomes better and robust when you have multiple data, right? So then you are trying to test the data set that is collected in Jabalpur versus the data set collected in Delhi. So then you are very different conditions, right? So that is the whole idea why we use multiple data sets for verification. So if the network knows only the data from Jabalpur, if you validate it on the Jabalpur data set, then your data is very similar, right? So you might end up with getting very high performance. But then if you go and use it in Delhi, then the network might start. So it's good to test the network on multiple and diverse conditions. Did I answer the question? Yes, that's always good. So train with one data set and validate with a different data set. Then you know, typically in the field, this is what is called as generalization problem, right? So you have one data set where the network performs extremely well, and then you take it to a different data set, and then you start seeing that the network starts failing. The accuracy of 90% here might drop down to 60%. And this is a bad scenario, right? Which is exactly what would happen if you're going to tomorrow, if you're going to create your own networks and try to sell it to a different country. So you have trained the network in India, and then you sell it to some other country, let's say China, and then it starts failing, which is not okay. So this is a bigger problem. It's called generalization problem. So one way to deal with generalization is to show multiple different data. To collect the fingerprint data set? Yeah, yeah. No, there are multiple ways. So today in the second part of the lectures, I'll discuss this fingerprint itself. So there we will show all different kind of capture settings. Easily is very very tricky. Many subjects you can. Yeah. So the second part we will focus purely on the fingerprints. Yeah. So everybody were able to run at least to verify the performance. Did you give your own images and check what's happening with that?